here is the Chapter 4 pre-quiz key, and we are going to go ahead and go through this. First question is, I'm taking two functions. I have f function, I have g function. I want to find if they're inverse of one another, so I'm going to use the definition. And the definition says that if g of f of x, so it looks like this, is equal to x, and so it's actually both of these, and f of g of x equals x, then these two functions are inverses of one another. Right, so I had to put this one into this x, and then I have to do vice versa. Okay, so let's go ahead and do this. So this one would be f of g of x. So I'm plugging in g into f. Another way to look at it is f of, like this, like that. That's another way to look at that. So I'm plugging in whatever inside the parentheses is what you're plugging in for x, right? So here I'm plugging in x into g, and then I'm plugging in what g of x is, that's this whole equation, into f, right? Okay, so here we go. So g into f. So here's f. 1/2 of what my x is. Well, my x is 2x minus 5. And then I'm adding 5. Okay, so I'm going to plug that in and see if I get x. So I distribute, and I get 1x minus 5/2 plus 5/2. Well, this does not equal x, right? Does not equal x. So since it does not equal x, that means that these are not inverses. So I don't even have to do this top one, g of f of x, because this first one did not equal x. So not inverse functions. Okay, let's move on to the next one. So another way that you can do this is to take one equation without using the definition. So this one doesn't say I have to use the definition, right? So another way to do this one is to take this equation and find the inverse of it. Okay, so that means switching my f of x to y, switching my x's and y's, and then solving for y. So let me write that up here. So x minus 3 equals square root of y. Square both sides. Change the color again. So then I'm going to square both sides. So that is y is equal to x minus 3 quantity squared. And is that what my other function looks like? Yes. So that is equal to g of f, or g of x. So yes, they are inverses of one another. Right? Because I turn this one into its inverse, and the inverse is that one. That would be, then they're inverses of one another, right? Yes, inverses. So turn f of x into g of x. Okay, now this one asks, are these functions one-to-one? So remember, for it to be one-to-one, we can use a couple different things. One-to-one means that for every x there's one y, and for every one y there's one x. So we could do the vertical line test. Just shows if an equation is a function or not. Vertical line test and horizontal line test. And what the horizontal line test does is, if I do the horizontal line test, that will tell me if the inverse is also a function. Okay, so when I do the inverse, I switch my x's and y's. So if I'm doing the vertical line test, right, if I do the inverse, that would be a horizontal line, right? The inverse of a vertical line would be a horizontal line. So in order to prove that it's one-to-one, we have to do vertical line test and horizontal line test. Okay, so that's one way to do it. Another way to do it, so that's one way for the one-to-one. Another way to do it is you could graph it, right, and then do both those tests. The second way to do it is to put f of a equal to f of b. What this means is basically that my y's are the same, right? My y is the same y. f of a means your y, f of b means a y value, your answer, and then if that's true, then a would have to equal b, right? Because I can't have the same y go to two different b's. I can't have one y, say 4, it can't go to two different x values, right? That would not be 1 to 1. Okay, so if I can prove that, this is how I prove it, by setting my y's equal to each other and then solving for a equals b. So you can do that, whichever one works best for you. So if I put f of a equals f of b, then I can do f of a would be 2a plus 1. And set that equal to f of b. F of b would be 2b plus 1. Now I'm trying to solve is a equal b. Subtract 1 from both sides. Oops, equals 2b, divide by 2, divide by 2. And we get a equals b. So for a here, letter a does equal b, so yes, 1 to 1. Okay, for b, if I could graph this, right? And if I graph this, we should know that this is a U shape, right? It's actually, yeah, it's something like that. So this fails the horizontal line test, so we know this is not 1 to 1. Done. Okay, so no. Or I could set a equal to b, or f of a equal to f of b. That'd be b squared minus 1. And then I can go ahead and add 1 to both sides here, and I get a squared equals b squared. So you might think they're the same, right? But when I square root both sides, I get a equals b. But because I square root, it's a plus or minus, right? So this is a no. No, not 1 to 1, because I could have a positive a equals a negative b, or I could have a negative a equals a positive b, and they would not be the same. Okay, so here is c. Let's just go ahead and set f of a equal to f of b, because if you know the graph of this, then you're okay. If not, then you could graph it out by plotting points, right? And graph it and then see what you get. But remember, whenever I square root something, I have a plus or minus, right? Or sorry, this should be b squared, or b plus 2. Now, there's some different looks that you could do with this, because if we're talking about square root, we always have a plus or minus, right? So that could give you an indicator that this is probably not going to be 1 to 1. And a square root function looks like this. But if we look at just the principal square root, we're only looking at the positive square root. So like the square root of 16 is not plus or minus 4, it's just plus 4. That's called the principal square root. Then it would eliminate this bottom row, and then it would be 1 to 1, because this continually increases. It continually goes up. It doesn't flatten out here. It continually goes up. So if we're looking at the principal squared root, then it would be 1 to 1. And you can say that if you want to say that, that's fine, but you would need to say yes it is, because we're looking at the principal squared root. Okay? But in all their circumstances, we're gonna go ahead and take the full square root. So this does not pass the vertical line test, right? And because this square root does not pass the vertical line test, what that says is the inverse would not pass the horizontal line test, which it doesn't, and we can see on B, right? The inverse is squared, and it does not pass that horizontal line test. Okay, so if we set equal to B, we can go ahead and square both sides. And so we get a plus b equals b plus 2. And here, if I add plus and minus out front, that would matter, because when I square a positive, I get positive. When I square a negative, I get negative. So then we can subtract 2, and we do get a is equal to b. That's why we have to identify if is it a principal square root or is it the whole square root. Because yes, we get a equals b here, but we know if we're talking about the whole square root, that means it doesn't pass the vertical line test, right? And yes, when I square a positive or a negative, it becomes positive, right? That is true. But I don't know if this inside is a positive or a negative. I don't know. I don't know if this side is a positive or a negative. So that's why, even though it comes out to a equals b, we need to decide, is this a principal square root or is it just a square root? And so you just need to identify. You could really go with, you could say yes, it is. if it is a principal square root. Or you could just say no, because it's just a square root. Okay, so really it could be both here, depending on how we want to define the square root. Okay, it's kind of like with restrictions. Okay, so here's d x cubed plus 1. So if we plug in our a, and we can see that this is a cube, so we think, oh, automatically cubed, right? It looks something like this, right? That would be 1 to 1. But not all, just because it's x cubed doesn't mean necessarily it's all 1 to 1. Now if it's just a plain x cubed plus your constant, then it will be always 1 to 1. But if it's x cubed plus x squared minus 2x plus 1, then it's not going to be, right? Because then it looks like this. So it's not going to pass the horizontal line test. Okay? So just make sure you're looking at what type of cube is it. Is it a cube plus a constant, or is it a cube plus more terms in there other than the constant? And if it's that case, then it's not going to be 1 to 1. Okay, and again, you can put your a and your b in there. B, not a. So an a and a b, and then you can subtract. So we get a cubed equals b cubed. So here, when I actually cube root both sides, I can cube root a number and get that. So if I say if I cube root 8, the cube root of 8 is positive, right? Well, the cube root of negative 8 is negative. So here there's no plus or minus out front, right? So a does equal b. So this one does pass. Yes, 1 to 1. So coming back to this one, C, just make sure you need to say, don't just say yes, or don't just say no, just explain what type of root are you doing. Are you doing a principal squared root, or are you doing just a square root? Actually, if you say no, then you can just leave it as no, okay? But if you say yes, you need to say yes. Why? Because it's a principal square root. You're only looking at the positive square root, the positive answer of a square root, not both positive and negative. So if you say just no, I'm okay with that. But if you say yes, then you need to say you're looking at a principal square root, okay? Okay, so horizontal line tests tell you about the inverse. Well, here's my function. Right, it's a square root function, so it looks like this, right? So we know if we do the horizontal line test that it passes, right? It passes. So if I do the inverse, that would look like this. So here's the function, here's f of x. Well, the inverse, f inverse of x, would look like this. Right? It looks like it is the squared. And that, I wouldn't do the horizontal line test because I have to do the inverse. The inverse would basically just be turning this one like this on its side, and that would become, instead of the horizontal line test, it would become the vertical line test. And what does the vertical line test tell us about an expression or an equation? It tells us if it's a function or not. So what does the vertical line test tell us about, the vertical line test on this tell us about this inverse? Well, the vertical line test on a function tells us if the inverse is a function or not. Okay, so the horizontal line test on a function will tell us that if the inverse is a function or not. Okay. All right, find the inverse of this one on number 5. That means we got to switch our x's and y's, or you can wait to the end to do that. That's fine. Then go ahead and solve. So we get square root of x is equal to 2y plus 1. Subtract 1 on both sides. So we get square root of x minus 1 is equal to 2y. Go ahead and divide by 2 on both sides. I'm kind of like doing this all at once. Divide by 2 on both sides. Sorry there, I was kind of just doing that for the benefit of those people that are just going to look at the answer key. So you could leave it like that, and then switch your y to f inverse. So, oops. So that'd be f inverse of x is equal to, and you can switch the places of these. You could let f inverse of x be on the left. You could write it like that, or you could write it like this. Square root of x over 2 minus 1/2. Or 1/2 square root x. That'd be okay too. Okay, so this one, you can switch the x and y's. You can go ahead and then square root both sides, or square both sides. Right, that's me squaring both sides. Then go ahead. Oh, I forgot. I didn't switch that to y. Sorry. y at 1 x squared plus 1 equals y. Then switch that to f inverse of x. Okay, so there you go. Okay, now we're moving on to logarithms. So we talked about one-to-one, talked about inverse functions, finding inverse functions, as well as proving that two functions are inverse. Now we're doing logs. So we want to switch this exponential problem to a logarithmic problem, or logarithmic form. So that means keep the base the same, put your log in there, log of the base. Now just this 3 and 27 switch places, so 27 goes with the base, and the exponent 3 goes as the answer. And then we can read it, right? Log of 3 of 27 means 3 raised to 3 equals 27, right? So that's my logarithmic form there, like this. Log of base 3 of 27 equals 3. Okay? So we switch places with those because that's what logarithms and exponentials are inverse one another. Okay, now expanding the logs. First start with division, right? Whatever's in the denominator, we're going to be subtracting. Whatever's on top, we're going to be adding. Okay? And we're keeping all that same base. So we're going to have log with that same base of my top minus the log of the bottom. Now some people will be able to just jump straight to the very end from this, and that's great. But I'm just doing it a little bit at a time. Now I have multiplication in here, right? So I have to separate the multiplication. And when I'm taking the log of a product, then I can separate that to the addition of two logs with the same base. So same base 3 of z squared. Now here I'm minusing this whole log, so I can put this in parentheses, or when I separate it, these two, since they're in the denominator, they're both going to be negative logs. Okay, so I can keep that in parentheses. And then when I'm multiplying, when I have a product of a log, I can separate that to the addition of two logs with the same base. Okay, so I can keep that in parentheses, or I could have just distributed that to begin with. So now I'm going to do two things at once here, since I'm kind of running out of room. Okay, I'm going to, well, maybe I should raise this up a bit. Okay, so raise it up a little bit. Now I'm going to simplify. I'll just go ahead and distribute that negative, and if you can look here, this log base 3 of 3 is 1. So this is actually 1 plus log 3 of z squared, log base 3 of z squared, minus log base 3 of x, plus, oh, I'm going to distribute the negative, sorry, minus log base 3 of y cubed. Now we can go to those power properties. When I'm taking the log of a number that's being raised to something, I can rewrite that exponent as being multiplied by the log. And these log properties are very similar to our exponent properties, our exponent properties. Z, I'm going to put a z like that. Okay, minus log base 3 of x minus 3 log base 3 of y. Okay, so that's my final answer like that. Okay, so that's expanding. Now condensing. When I condense, what I want to do is I want to turn it into one single log. Okay, so I want to turn this into one single log. And my base is 3, so if you want to, down at the bottom, I'm going to get log of base 3. Okay, so first thing when you condense, you want to do the multiplication, something multiplied by a log first, that exponent or the power property of logarithms. So this is being multiplied by a log, so that is now going to become an exponent on what I'm taking the log of. Same with this next one. I'm multiplying by 2 here. So that's going to become an exponent on what I'm taking the log of, y. Okay. Now I can rewrite this as a square root, right? Because a half power is a square root. Now on the next one, whatever I'm subtracting is going to go in the denominator, right? Since I'm subtracting these two logs, that means I'm going to create a fraction, a quotient. That's the quotient property. Whatever you're subtracting will go in the denominator. Whatever you're adding, even though this is after the subtraction sign here, I am still going to put this one right here in the numerator because I'm adding, right? What you could do is if you would undistribute a negative from both of those, it'd be negative log base 3 of y minus log 3 of z. And then you could go ahead and put both of those would go, you would have to rewrite this, which would be a fraction, and then you'd be putting both of those in the denominator. It would look something like this, so c over b over a, like that, and that's which happens, this just flips, right? So it becomes ca over b. Probably on all that just didn't make sense right now, so I'm going to erase all this. And okay, so we'll just continue after I erased all that. But so whenever you have a negative log, that's going to go in the denominator. Whenever you have a positive log, that stays in the numerator. Okay, and I'll show you maybe after this a little easier way of kind of doing it. So this z is going to go on top because it's adding, and this y squared is going to go on bottom because it's subtracting the log. So there's my answer, just like that. And then I'll show you real quick. So if I have 1/3 times 2, isn't that 2/3, right? So if I could do this separate and say the log base 3 of square root of x over y cubed, or squared, sorry, y squared, right? That's what it looks like when I just do the first two. And then I'm adding log 3 of z, so that means I'm multiplying because I'm adding, right? So that would be log base 3 of the square root of x over y squared times z. And just like this, when I take a fraction times by just a whole number, isn't that whole number always in the numerator? So I multiply numerator. So that's why I ended up with z in the numerator right here on this problem. Okay. Okay, so we touched on logarithms, rewriting logarithms of exponentials, and also expanding them and condensing them. Now we're going to go solve some exponential equations. So when we do that, we have to keep the base the same. So I need to rewrite 16 and 8 with the same base. So 2 to the 4th is 16, and 2 to the 3rd is 8, right? So that would be 2 to the 4th is now being raised to the x, because that's 16, and 2 to the 3rd is now being raised to the x plus 1, because that's what 8 is. Now when I raise powers to powers, I multiply. So that's 2 raised to the 4x, and this would be 2 raised to the 3x plus 3. Make sure you distribute that to both of them. And now since the bases are the same, now our exponents must be the same, because if we're equivalent, meaning they're the same, right? So since our bases are the same, exponents have to be the same. Why did I do that? But that's okay. Let's not do that. Let's subtract 2x from both sides, not subtract 3. So then we get 2x equals 3 divided by 2 divided by 2. X equals 3/2. And you can plug that back in the original and then add 1 to the right side and take 16 to the 3/2 in your calculator, which would be the square root of 16 times itself 3 times. So that would be square root of 16 is 4, and 4 times itself 3 times. And then on the right side would be 3/2 plus 3/2 plus 2/2, so that'd be 5/2. So that'd be taking the square root of 8, which I don't know, so I'd have to do that on my calculator, and then times in itself 5 times. And you can see that those will end up being the same. So this is true. X equals 3/2. Okay, on the next one, it's a little bit different. I saw a few people do it different ways. Some people rewrote 25 as 5 to the -3, and then they get that 5 in the denominator because this is 5 is in the denominator. Or some people rewrote the 5 and rewrote that as, so then it would be 125. So they rewrote that as 5 to the negative 1. And then this side would be in the numerator, and then we'd still rewrite 125 as 5 cubed. So either way, so you can rewrite the right side as 5 to the negative 3, and that's being raised to x minus 2. And then this one, I can rewrite that one. I could leave that 1 over 5 to the x. So then really this is then 1 over 5 positive 3 now raised to the x minus 2. So I can move it from top to bottom by changing the sign of the exponent. Now when I raise powers to powers, they are the same. And since my numerators are the same here, that means my denominators also have to be the same, so I'll set my denominators equal to each other. Now when I raise powers to powers, I multiply, so make sure you distribute that 3 to both of them. That's where I would check first. If it doesn't work out, I would check that first. Well, make sure your bases are the same first, and then make sure you distribute your powers to powers there. So now I can go ahead and add 6 and subtract 1, so we get 2x is equal to 6, divide by 2, x is equal to 3, and you can plug this back into the original and make sure it works, right? 3 minus 2 is 1, so we get 125 equals 1 over 5 to the 3, which is 125, and that's on bottom. And that doesn't work out, right? Because the top was 125 and equals 1 over 125 is not correct, right? So I have to go back through, and I can see that I really need a negative 3 here. And since I need a negative 3, that must be a negative 6 here. That means that should be a positive 6 here, and that should be a positive 6. So somewhere I went wrong, and it's probably right here when I move this 3 to the bottom down here. I probably should have distributed that and got a positive 6 here. Nope, what I did wrong was right here. I should have left this. I shouldn't have moved it down, because this is not correct. So this should stay as 5 to the negative 3 raised to 2x minus 1, or minus 2. It should stay there, and it should equal 5x, or 5 raised to the x, sorry. Because this right here is 1 over 125, so it is in the denominator. So this right here already is in the denominator, so if I move it like I moved it right now, that doesn't look like that. This is already 1 over 25. And then so I changed that sign so it would be 1 over 25. Well, this already says that because of that negative. So I screwed that up, wasted probably 2 minutes of your life that you're never going to get back. So when I write this right here, that is just this in green down here, right? It's just without, it would be already written like that. So there now we can go ahead and solve this, set those numerators equal to each other, make sure you distribute, and then we can go ahead and solve this to get negative 3. Okay, so I just went ahead and rewrote it. My exponents are now set equal to each other. I can add 6 to both sides and add an x to both sides. So we get 4x is equal to 6. So it's actually x is equal to 3/2. Now definitely I should check this one because I messed up so much. At least the people just looking at the notes will see that it works. So sorry for wasting your time, and you probably did it yourself and wasted 10 minutes. If I could rewind this and re-record, I would, but I can't. Okay, so we plug in our exponents, then we're going to take 3/2 minus 2, which is 4/2, so that's minus 1/2. 4 halves. 4 halves, and so we minus that, we get minus 1 half, which brings it to the bottom as a positive 1 half equals 1 over 125 to the 1 half and 1 over 5 to the 3 halves. So we need to make sure if these are the same, which we can rewrite 125. So there's 1 over 5 cubed raised to the 1 half equals 1 over 5 to the 3 halves. Multiply, raise powers, multiply them. Look at that. And we get the same exact thing, so we know that we were wrong to begin with, and we came back and we made sure we got the correct answer. That is the value of checking, even if it takes you extra 10 minutes and it's annoying. But that's what happens sometimes. Okay, change the base formula. Go ahead and take the log of the top over the log of the bottom, and you're done. So around 2.7-ish, something like that. And then, or you could do ln. You could do ln of 20 over ln of 3, and that would still be 2.7-ish. Okay, investing. So if I invest $27,000 at 12% annual interest, compounded continuously, how much will be in the account after 35 years with no withdrawals? Okay, so this is kind of like, hey, if you can invest $27,000 into a retirement fund when you're young, like in your 20s, and you let it go for 35 years until your retirement, how much money could be in your account at the end? How much money could you have for retirement if you could just put $27,000 in when you're 20, and then when you retire at 55, how much money could you have in your account? Well, it's compound continuously, so that's A perk. How much money am I investing? That's $27,000. That's quite a bit, right? Now we can go ahead, ease the button on your calculator so we don't have to enter in an E. R is our rate. We need to change that to a decimal, so we get 0.0, well, actually 0.12, right? Make sure I move my decimal correctly. Times by time, and it's 35 years. And raise that to the E. So I could do those separately. I could multiply that and then raise it to the E and then times it by my 27,000. Or I can enter that all just like that in my calculator, and we'll see what we get. So here we would get the amount in our account after 35 years for our retirement. We would get $1,800,503.94. So if you can invest $20,000 into an IRA for 35 years and not take from it, when you retire, you would have about $1.8 million. Now that interest rate is pretty high, but that's the average interest rate. If you just leave in your money, it might go up and down, but it usually averages every 10 years about 12%. Okay, so here's another one. How about $15,000 at 5%? Compounded monthly, so that means we're not using A perk anymore. We're using the 1 plus R over N times by our principal raised to the N times T. N is how many times it's compounded in a year, so that's 12. So we have 1 plus our rate, which is 0.05 over 12. And then once we add those together, we're then going to raise it to N, which is N, which is 12, times how many years we were doing this for, and that is 3 years. So that is 36, right? 3 times 12 is 36, and then we'll times that by our principal is 15,000. Okay, so you can do these individually, or you can do it pretty much, you can enter it like this on your calculator and you will get your answer as well. Okay, so when I enter that in my calculator and I take 0.05 and I divide it by 12, I get 0.04, and then it keeps on going. Well, I want to keep that number in my decimal. Okay, so here, I'll just switch it. So I want to keep that number. So here it is. Here's that number in my calculator, and what I want to do is I want to add 1 to this, okay, and then I want to raise that to my 36, right? How many times I'm doing it for. So I got to figure out on this calculator kind of how I do that. Okay, so then this is the answer I got. I use this XY button here. So, and now I'm going to have to times that. So I had my 0.1004 blah blah blah, and then I raised that to 36, and now I'm going to times that by 15,000, sorry. And so there's my answer, 17,422. So 17,422 and 8 cents. So that's why I didn't want to round that and use 0.004. So I don't want to round here. So don't round. Keep that in your calculator, because if you do that, then you miss out on some money. Well, how long will it take for the money in an account, in any account, to double with the interest rate at 3% compound continuously? So compound continuously, we're going to go ahead and use APERT because it's compound continuously. Well, how much money are we investing? Well, all I know is I want double. What double of what? Double of my principal. So wouldn't that be 2p? So the amount in the account at the end I want to be 2p, double the principal. I'm investing the principal, and I have my rate and my time. So my rate, it's okay that you don't know your principal. Your rate is 0.03, and my time is, I don't know. I want to figure out how much time will it take to double. Well, go ahead and solve this for t. First, we need to get rid of multiplying by our principal, so we divide. That means our p's are now gone. So we get 2p is equal to e raised to 0.03t. Now, how do you solve exponentials? We switch it. When we want to solve for the exponent, we need to switch this to a logarithm, right? So we need to switch this to a logarithm. And so we go ahead and do that, and it's log base e. And then we can switch these. We can switch these two. So 0.03t. And log base e, that is ln, so ln of 2. Now we can divide by 0.03. And again, when you press ln of 2, keep that number in your calculator and just push divided by 0.03, and then we'll have our t. Okay, so in your calculator you take your ln. Mine's a backwards calculator, what I like to call a backwards calculator. So I just took ln of 2, there it is. Now I'm going to divide that by 0.03, and there's my answer, 23 years. And I'll round it to years, right, because it wants to know how long. So I don't know what 0.1 year is, so I'll just round it to 23 years it's going to take. So 23 years, right? Okay, graphing, we're graphing exponentials, so we need three things. We need a vertical asymptote, we need 2 points, and we need the shape. All right, those are the points that we need, or the things that we need. Okay, so our vertical asymptote is really y equals k. So that means y equals -3 is our vertical asymptote. So -3, 1, 2, 3. Put that in there. Now we just need our 2 points. So 2 points, we can just make an xy table. What are some good x's to pick? And we want x's, you can pick any x you want to, but sometimes we want to pick x's so that our exponent will be both 0 and 1. So if I pick the exponent as -1, then I will get an exponent of 0, so that'd be 2 raised to -1 plus 1. See how we get 0 there? And then we can take 2 to the 0 minus 3, which equals 1 minus 3, which equals -2. So -1, -2. So -1, -2. So there's my point. Now another one to pick is 0, because 0 plus 1 is 1, and 2 to the 1 is 2, and 2 minus 3 is -1, so 0 minus 1. Now we can grow our shape, goes close to the asymptote, but doesn't cross it. This one, it does continue to grow up, it doesn't, or grow up, it continues to go up, it doesn't flatten out, and it doesn't come back down. So it is a continuous function. All exponential functions are continuous, same with all logarithm, which is next. So we want to do our horizontal asymptote here, right? And then we want 2 points. And then we want the shape, right? Oops. 2 points and a shape. Okay, so first we need our horizontal asymptote, and that is always x equals our h, and h is always opposite of inside. So that'd be x equals a +2. And let's go back up here. Hopefully some of you guys noticed that I was wrong here. that I just graphed a logarithm, if anybody noticed that. So it is y equals -3. This would be x equals -3. So let's erase that. I still have these 2 points. Right. So let's go x equals -3. So make sure that you know which type of function you're dealing with. There is x equals -3. There are my 2 points at 0, -1, and -1, -2. Now I can grab my shape. So there, you know, if I was grading somebody's like that, they wouldn't get the point for the shape, but they would get the point for the 2 points, and they would probably get a half a point for the vertical asymptote. And I'm glad I caught that, right? So it's not the vertical asymptote you're looking for here. It is the horizontal, correct? You want the horizontal asymptote. And so the horizontal asymptote is y equals k. Now we come back here and say not the horizontal we're looking for. We're actually looking for the vertical. So people make mistakes, right? But what do we do after we make those mistakes? Makes a big difference, right? We got to keep going. You got to keep going. You got to keep trying. You don't just give up and shut off the video, right? I've wanted to do that a few times after my mistakes in this video, and then redo one where it's all perfect. Well, sometimes it's not going to be perfect, so might as well let you see that, right? All right, x equals 2. So let's go ahead and do our vertical asymptote at x equals 2. There it is. Okay. Now we need to find 2 points, right? So here to find 2 points, you could plug in any numbers you want to, right? You can think about what's some good numbers to plug in that I can take the log of base 3 of some number that I actually know. All right, I can use my calculator. I could do change of base formula, right, to go ahead and solve that. Some of you guys know how to enter that into your calculator and find those numbers. That's perfect. Just make sure you're probably going to have, you might have decimal answers, right? So make sure that you at least put what those points are, the coordinates of those points. If you're going to do decimals and you're going to round, at least put the coordinates of those points. Just don't put this like right there. Okay, there's a point. Give me the coordinates, okay? I'd rather you not use a calculator to graph this at all, because you can do it by hand. Okay, so some good x's to pick would be 3 and would be 4. Or sorry, 5. Those are some good x's to pick, right? Because when I take my h and I add 1 to it, when I take my h and I add 1, I would get 3. And when I would take my h and add my a, my base, I would get 5, right? And those are some good x's to pick. Because when we plug those in, when I plug those numbers in, remember, anything 3 raised to what is 1? That'd be 0, right? And then this would be 1 for my y, because 3 raised to what is 3? It would be 1. So those are my 2 points I can do. And I'll show you right here. Oh wait, I have to add 1 to it, right? So I'd have to add 1 to these, and add 1 to these, because that's plus 1 right here. So that would be 3, 3, 1. So 3, 1, 3, 1, and then 5, 5, 2. And then I would connect them. It continues to go up here, doesn't flatten out. So there's my graph. Again, if you don't get whole numbers here or integers, then make sure you label those points. But here I have whole numbers, so you don't need to label those. I can see on a graph what you do. Okay, so let me show you what those might look like. So 1 plus log base 3 of 3 minus 2. Right, those parentheses matter. I got to do what's inside the parentheses first. So that would be 1 plus log base 3 of 3 minus 2, which is 1. And this says 3 raised to what is 1? Well, that would be 0. And then 0 plus 1 is, that's for that one, is 1. And then this one would be taking 1. Oops, I erased that one. There. For those people that are just looking at the answer key, I want to make sure that it's kind of legible. So this one would be 1 plus log of 5 minus 2 with base 3. So that is 1 plus log of base 3 of 3. And 3 raised to what is 3? That'd be 1. And then 1 plus 1 is 2. So that one goes to that one. Okay, another way to do it would be to switch this to a exponential. And in order to do that, first you need to get this log by itself. So if I subtract 1 on both sides, y minus 1 equals log base 3 of x minus 2. Okay, then I can go ahead and switch it to exponential, base 3. Now these switch places. So I get 3 raised to y minus 1 equals x minus 2. Okay, now we can solve for x here. So we can get 3 raised to y minus 1, and then plus 2. So now here we would pick y's. You pick y's first. Solve for x. Alright, that's what you do there when you do this type. So this would go with this one. Or actually, let me point. That would go for that one right there. That I pick my x's first, or pick my y's first, and then solve for x. So a good one, right, would be 2, would be 1, would be a good y to pick, because then I would have an exponent of 0, and anything raised to 0 is 1. Isn't 1 one of these answers right here? And then another one would be 2, because 2 minus 1 is 1, and 3 to the 1 is 3. And isn't the second y here 2? So that's why those are kind of nice. Alright, so that's it for the video. I again apologize about some of the problems in here that I totally kind of screwed them up, but I did go back through. If you have any questions with these, let me know. You can go back over them before your quiz. Again, I apologize about the length of these. If I could edit them, actually, if I could edit them, I probably wouldn't edit them anyways, because it takes a lot of time and I'm wasting your time right now. Alright, all done. Oh, real quick, since you wasted all this time of, almost 50 minutes, and I kind of messed that up for you, maybe I should give a bonus problem on the quiz, something that's maybe interesting. Maybe let's look at what problem did I mess up on the video. Let's go with that question. What problem did I mess up on the video would be the bonus. Make sure to not tell anybody. I mean, you guys put in the extra time of watching these videos, and now somebody gets extra credit because they just are your friends or something. Like, you spent the time watching the videos, not your friends, so don't pass this answer out to other people. Right, so which one did I mess up on? This one, right? This second one, 10B. So the answer to the bonus would be 10B. Okay? So the bonus is, what problem did I mess up on the video? And we'll go with 10B, even though I kind of messed up with the logarithm 1, 2, but I kind of corrected that pretty quick, right? Well, okay, so 2 points each. What 2 problems did I mess up on the video? 10B for 2 points, and then problem number 15 for another 2 points. So you can get 4 points of extra credit if you watched all this video. Okay, please don't share this with anybody unless they watch the video. Okay, all right, have a great day. Get ready for that quiz. Study, 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 study.